In actuality, digital signatures are products of more advanced elliptic curve math, which result in R and S integers that wallets and nodes can decipher and use to verify transactions. If you want to get the full details of what this confusing screen is, go to this YouTube video, and it's a really, really good detailed explanation. If you look at the red highlights, this is what you should really focus on with this. So as you see here, signature generation. So this is the process for generating the digital signature. Like I said, it results in R and S integers. So the signature is R and S. And to be very clear, I took this screenshot from this video. I want to give my guy his full credit. So as you see here, S equals the hash of the message. As I've stressed to you through this digital signature lesson, the message is a part of the digital signature. The sender, the receiver, the amount being sent, the date and timestamp, different things like that are a part of the message. Those things get hashed together, as we discussed in previous videos, what hashing is. So the hash of the message is directly included in the signature generation portion, and so is the private key. So the hash of the message and the private key are used to create this S integer, which is a part of the signature. Now, look at the signature verification portion. This is what the nodes do to verify that the transaction that's being sent is the private key holder the person that actually sent this message, or is somebody trying to send a corrupt transaction? Is somebody trying to send funds that they don't actually have? So again, look at the red highlights here. Hash of the message is included in the signature verification process as well. So the hash of the message is public information. When a transaction gets submitted to the blockchain, the hash of the message is a piece of public information that gets submitted with the transaction. And then if you look at the second highlight, the public key. So the public key is used in the verification process. Now, if you look through all of this, you don't see the private key anywhere, right? The private key is only used in the generation portion, and then the public key is used in the verification portion. And since the public key and private key are directly linked, as we have explained throughout this lesson, the public key can be used to verify the private key without needing to know what the private key is in order to verify it. Now, again, like I said, this is confusing and more advanced cryptography. You got -1 exponents, and you got S raised to the -1 mod n, different things. So like I said, check on over to this YouTube video here if you really want to get an in-depth lesson on what exactly all these components are, or if you just want to get the surface level stuff that I'm explaining, you should just really take away, as I've explained, the the digital signature generation portion includes the hash of the message and the private key. So this is the sender doing this part, or the sender's wallet doing this part. And of course, the sender's wallet knows what the private key is. The sender's wallet created that private key. So when the sender creates the message, it gets hashed via the wallet software. The wallet uses the private key to create the digital signature, which gets sent to the blockchain. The nodes then use the hash of the message along with the sender's public key, because as I said previously, the public key gets sent along with the message as well. So the nodes use the hash of the message and the public key to verify that the signature is valid. If you look here, it does these steps to come up with these R and S, right? So the signature is R and S integers. The final verification process goes through these steps to come up with these other integers, x2 and y2. So the actual verification process says if the R integer here equals x2 mod n, then the signature is valid. So this is what the node is doing. The node does all of this math to make sure to check this line here. Does R equal x2 mod n? If it does, then it's valid, meaning the public key that came with the transaction is directly linked to the private key that created that digital signature, and it will let the transaction go through. If these do not equal, then that means the public key used to verify the signature is not linked to the private key, meaning a hacker or somebody with false intentions is trying to send a transaction that he or she doesn't own the private key to. And as I said in the previous slides, the Bitcoin script specifically says that the public key used to create the address from which the coins are being sent must be directly linked to the same private key used to create the digital signature for that transaction in order for the funds to be released. In other words, the digital signature provided has to have been made with the private key that is linked to the public key of the address for the coins. And here's, for my more visual people, one more example showing you all of this. And if you notice, the 4 same red highlights are here. So it's consistent from this slide showing the elliptic curve version of what's going on. And here's the conceptual visual version of what's going on using the exact same elements that the elliptic curve aspect actually uses. So here's the electronic file or data or transaction gets hashed. So we have the hash of message here that is then encrypted with the signer's private key, which produces the digitally signed transaction. So the transaction data with the digital signature. We jump down to the verification aspect. You have the digitally signed transaction. So that gets broken down into 2 different steps. The node or the verifier would take the file data and hash it to get hash of message. So again, hash of message is on the verification side and hash of message is on the signing side. Just like we have here, hash of messages in the generation portion and hash of messages in the verification portion. And then here, the encrypted signature, so the digital signature, is decrypted with the sender's public key to return another set of data. If these 2 match, if the hash of the value here matches the hash of the value here, the hash of message, then the digital signature is valid. So everything we have covered so far only takes us to the verified but not mined portion of the blockchain compound. It's important to understand that just because a transaction is verified, it doesn't mean it's confirmed on the blockchain. There's a multi-step process to make all of that happen. First, the transaction is created by the wallet and submitted to the blockchain, as we've covered. Then the nodes verify the digital signature and the unspent outputs, as we've covered. Then the miners must include the transaction in a successfully mined block for it to actually be added to the blockchain, which will be covered in the next video.